80%, that's the number. Not a small reduction or marginal improvement, but a collapse in cost so large it doesn't fit comfortably within what people expect from housing. Because right now, the direction is clear. Energy bills rise. Maintenance costs stack. Systems get more complex, not less. Heating, cooling, ventilation. Layered systems, each drawing power, each adding dependency. And yet, inside that trend, there are houses operating under completely different conditions. Homes where monthly bills don't just shrink, they almost disappear. That's where the contradiction begins. If something can reduce operating costs this dramatically, it should spread, scale, and become standard. But it hasn't. And that's what makes the number feel out of place. Not because it's impossible, but because it exists without consequence. This house, built from recycled materials, saves 80% on bills. Why is it ignored? Step inside and the difference isn't loud. There's no visible machine doing the work. No constant hum of systems switching on and off. No aggressive airflow forcing temperature changes. Instead, the space feels stable, not artificially adjusted every few minutes, just steady. The temperature holds, shifting slowly but never spiking. The air moves gently. Light enters in a way that feels intentional. Even the silence feels different. Nothing signals advanced technology. If anything, it feels simpler. And that creates a contradiction. Because in modern housing, simplicity usually means compromise. Less comfort, less performance. But here, the opposite is happening. The house is doing more by needing less. Look closer at what it's made of, and the assumption breaks again. Recycled materials, not decorative accents, not aesthetic choices, but the structure itself. Walls formed from compressed earth. Discarded tires packed and stacked into dense layers. Bottles, glass, and metal fragments embedded within the building envelope. At first glance, it doesn't match the image of efficiency people expect. Efficiency is supposed to look engineered, clean, standardized. This looks improvised. But that appearance hides what the house is actually doing. These materials aren't just replacing conventional ones. They're changing how the building behaves. They alter how heat moves, how energy is stored, how the interior responds to the outside world. And that shift is where the real performance begins. Think about where most of the cost in a home comes from. It's not the walls. It's what the walls fail to do. Heating systems compensate for heat loss. Cooling systems fight heat gain. Insulation slows the exchange, but rarely stops it. So energy flows constantly, and systems respond continuously. That's where the bills come from. Not from one event, but from constant correction. A house in that sense isn't stable. It's always adjusting. Now remove that assumption. What if the structure absorbed those changes instead of reacting to them? What if heat was delayed, stored, and released slowly over time? What if temperature wasn't forced, but held? That's the shift. And it begins with the materials themselves. In these homes, the walls are thick, dense, and heavy. That weight isn't incidental, it's functional. During the day, outer layers absorb heat. But instead of passing it straight inside, that energy moves slowly, taking hours to travel through the mass. By the time it reaches the interior, outside temperatures have already dropped. The heat arrives late and often fades before it's even felt. The same happens in reverse when temperatures fall. The result isn't perfect insulation, it's a delay, a buffering effect, a smoothing of extremes. Instead of reacting to the environment, the house reshapes how the environment is experienced. And that alone removes much of the need for active heating and cooling. Now layer in the rest. Openings placed with intention, allowing natural airflow to move through the structure. Cooler air enters, warmer air exits. No forced systems, just pressure differences doing quiet work. Light is used strategically, entering during colder periods and avoided during hotter ones, guided by orientation rather than electronics. Water systems reuse what would normally be discarded, cycling it through simple paths instead of sending it away. Each element on its own isn't revolutionary, but together they form a system, a house that reduces its dependence on external inputs. And when dependency drops, so do the costs attached to it. So when someone says 80% savings, it doesn't come from a single innovation. It comes from removing the need for constant correction, from letting the structure carry part of the workload machines usually handle, from designing the house to cooperate with its environment instead of resisting it. That's the real mechanism, not a trick, not hidden technology, just a different starting assumption. And this is where the tension sharpens, because nothing here is theoretical. The materials exist. The physics is simple. The examples are real. These homes are already operating, quietly proving the reduction is possible. Which leads back to the question, if the cost savings are real, if the comfort is real, if the passive system works as intended, why does it remain on the edges? Why isn't this the direction housing is moving toward? Because to answer that, you have to stop thinking about houses as objects and start thinking about what they're expected to do, not physically, but structurally within a larger system, a system built on assumptions about energy use, maintenance, and continuous input. And once that perspective shifts, the answer begins to look very different. Before anything else, it helps to reset one assumption. Most houses are not designed to maintain comfort on their own. They are designed to respond. A furnace turns on when temperatures drop. An air conditioner activates when heat rises. Fans circulate air when it becomes stagnant. Every system waits for a change and then corrects it. That model works, but it comes at a cost. Because the moment you rely on constant correction, you also accept constant consumption. Energy in, adjustment, energy in again. Over and over. Now imagine removing most of that cycle, not by adding better machines, but by changing what the building itself does. That's where these homes begin. Instead of thin, lightweight walls acting as barriers, these structures use mass. Not decorative mass. Not superficial thickness. Real, physical weight. Packed earth, compacted soil, reused concrete fragments. Tires filled and stacked until they form dense structural units. Glass bottles embedded within layers, not for appearance, but to shape how light and heat move. At first glance, it feels unconventional, but the logic behind it is direct. Mass changes time. When sunlight hits a typical wall, heat moves through it relatively quickly. Insulation slows the transfer, but it doesn't fundamentally alter the behavior. The energy still moves from one side to the other, and systems inside the house must react to keep conditions stable. With dense materials, something different happens. Heat doesn't stop. It slows down. It enters the outer surface and begins to move inward, but the journey takes hours, sometimes longer. The material absorbs energy, holds it, redistributes it gradually, instead of passing it through in a single wave. So when the outside temperature peaks, the inside barely notices. And by the time the stored heat reaches deeper layers, the external environment has already changed. The system never needs to correct a spike, because the spike never fully arrives. This is often described as thermal mass. But the term can feel abstract. So picture it this way. Take a thin metal sheet and leave it in the sun. It heats up almost instantly. Touch it, and you feel the intensity right away. Now take a thick stone block. Leave it in the same sun for the same amount of time. It warms, but slowly. The heat spreads unevenly. The surface changes first, then deeper layers follow. Even hours later, it continues adjusting. That delay is the difference. One material reacts immediately. The other stretches the experience of heat across time. These homes are built around that second behavior. And it works both ways. At night, when temperatures drop, the stored warmth inside the walls begins to move back toward the interior, not suddenly, but gradually, just enough to offset the cooling air. So instead of sharp transitions, hot afternoons, cold nights, the environment becomes smoother, flatter, more stable. And stability is what eliminates the need for constant energy input. But mass alone isn't enough, because a heavy structure without control can become a problem instead of a solution. That's where layering comes in. In many of these homes, the dense core is combined with insulation placed strategically, not everywhere, but in locations that control the direction of heat flow. On the exterior, insulation can prevent stored energy from escaping too quickly. On the interior, surfaces are chosen to interact gently with the living space. The result is not just a barrier. It's a system of timing. Heat enters, pauses, redistributes, and exits, according to how the structure is arranged. And that arrangement is deliberate. Then there's airflow. In conventional homes, air movement is forced. Fans push it, ducts direct it, systems regulate it mechanically. Here, airflow is guided instead of imposed. Openings are placed to take advantage of pressure differences. Warm air, which naturally rises, is given a path to escape. Cooler air is drawn in from lower points. Windows are not just for light or view, they become part of a passive circulation loop. No switches, no motors. Just a continuous, low-energy exchange. And because the internal temperature is already stable, the airflow doesn't need to fight extremes, it only needs to maintain balance. Light plays a role too. Not in a decorative sense, but in how energy enters the space. During colder periods, sunlight is allowed deeper into the home. It reaches surfaces designed to absorb and store heat, adding to the internal reservoir. During hotter periods, that same sunlight is blocked by overhangs, angles, or placement decisions that prevent direct exposure when it would be harmful. The building doesn't just exist in its environment. It interacts with it continuously. Water systems follow a similar logic. In a typical house, water flows in and then out, used once, then discarded. In these systems, that flow is extended. Greywater water from sinks, showers, and other non-toxic uses is redirected through simple filtration layers. Plants, soil, and gravity do most of the work. The water is reused, repurposed, cycled instead of expelled immediately. Again, the goal is not perfection. It's reduction. Every loop that stays inside the system is one less demand placed outside it. When you step back and look at all of this together, a pattern starts to emerge. Nothing here depends on a single breakthrough. There's no central invention carrying the entire system. Instead, there are multiple small decisions, each removing a point of dependency. The walls reduce the need for heating and cooling. Airflow reduces the need for forced circulation. Light reduces the need for artificial adjustment. Water systems reduce waste and input cycles. Individually, each one lowers demand. Collectively, they reshape it. And that's where the 80% begins to make sense. Not as a claim, but as a consequence. Because if a house is designed to need less, the systems that normally generate costs simply have less to do. Energy usage drops. Equipment runs less frequently. Maintenance cycles stretch out. The entire structure becomes quieter, not just in sound, but in demand. So, at this point, the technical question is no longer unclear. The physics holds. The materials behave exactly as expected. The outcomes are consistent with the design. There's no missing piece in how it works. Which leaves only one direction left to look. Because if the system is this effective, if the reduction is this significant, then the limitation isn't inside the walls. It's somewhere outside them. And that's where the real friction begins. If the design works, the next step should be obvious. Refine it, standardize it, scale it. That's how most successful systems evolve. Once something proves efficient, it moves from the margins toward the center. It becomes easier to build, easier to finance, easier to approve. Over time, it stops being an exception and starts becoming the norm. But that shift hasn't happened here. Not at scale. Not in a way that changes the broader housing landscape. And the reason isn't hidden inside the materials, or the physics, or the performance. It starts the moment the house meets the system built around it. Begin with something simple. Approval. Before a house is built, it has to be allowed. That means codes, standards, requirements designed to ensure safety, consistency, and predictability. On the surface, that sounds neutral, necessary, even. But those systems are built around known patterns. Standard materials, standard methods, standard assumptions about how a house is constructed and how it behaves over time. Recycled material homes don't always fit those patterns. A wall made from compacted earth and reused components doesn't map cleanly onto predefined categories. Inspectors and engineers don't always have a direct reference point. The burden shifts from following a known path to proving something unfamiliar. And proving something unfamiliar takes time. Additional testing, additional documentation, additional scrutiny. Not because the system is trying to reject the idea, but because it isn't designed to process it efficiently. So what should be simple becomes slow. Then comes financing. Most homes aren't paid for upfront. They're financed through systems that depend on predictability. Banks assess risk by comparing properties. They look at similar homes, similar materials, similar market behavior. From that, they determine value. But what happens when there are no clear comparisons? A house built from recycled materials, operating with drastically lower costs, doesn't align neatly with conventional data. It's not just a different structure, it behaves differently over time. Lower bills, different maintenance cycles, different long-term costs. 3. From a purely logical perspective, that should increase its appeal. But from a financial perspective, it introduces uncertainty. And uncertainty, in lending systems, tends to slow things down. Approvals become harder. Terms become less favorable. Sometimes, access disappears entirely. Not because the house is flawed, but because it doesn't fit the model used to evaluate it. Insurance follows a similar pattern. Policies are built around known risks: fire resistance, structural integrity, environmental exposure, each one assessed using established datasets tied to conventional materials. When a house steps outside that framework, the data becomes less clear. Even if the structure performs well, sometimes better than standard construction, the lack of familiar benchmarks creates hesitation. Premiums can rise, coverage can narrow. In some cases, policies become difficult to secure at all. Again, not a direct rejection, just friction. Now step back and look at the broader system. Construction itself operates within a network. Suppliers produce standardized materials at scale. Contractors are trained around specific methods. Tools, timelines, and labor models are all optimized for repetition. Introduce something different, and that efficiency disappears. Specialized knowledge is required. New processes must be learned. Supply chains don't align as easily. The rhythm of construction changes. And when rhythm changes, so does cost. Even if the end result is more efficient, the path to get there becomes more complex, which makes it harder to compete within a system built for uniformity. Then there's valuation. Not just from banks, but from the market itself. Property value is often determined by comparison what similar homes have sold for, how they're categorized, how they're perceived. But a home that operates differently challenges those comparisons. If it saves significantly more on bills, does that increase its value? Logically, yes. But if buyers don't fully understand the system, or if there aren't enough similar homes to establish a pattern, then that value isn't always reflected clearly. The house exists between categories, not fully recognized for what it does. All of these factors, approval, financing, insurance, construction, valuation, they don't operate independently. They reinforce each other. If financing is harder, fewer people build. If fewer people build, there's less data. If there's less data, approval becomes slower. If approval is slower, costs rise. A loop forms, and inside that loop, anything that doesn't match the default model struggles to move. But underneath all of this, there's a deeper layer, one that doesn't show up immediately in permits or policies, but shapes how the entire system behaves. Most housing, as it exists today, is part of an ongoing cycle. Energy is consumed, systems are maintained, components are replaced, services are used continuously over time. Value doesn't just come from the initial construction. It comes from what happens after. Monthly bills, repairs, upgrades, replacements. The house isn't just a structure. It's part of a long-term flow. Now place a system into that environment that reduces those flows. A house that requires less heating, less cooling, less intervention, less ongoing input. From the perspective of the occupant, that's a clear advantage. But from the perspective of the broader system, something changes. The flow becomes smaller. Not eliminated, but reduced. And when that happens, the incentives that support the existing model don't align as cleanly. This isn't about opposition. There's no single point where the system pushes back. Instead, it's a series of small mismatches. A house that doesn't fit easily into approval frameworks. A structure that doesn't align with financing models. A design that reduces ongoing consumption in a system built around it. Each friction point is minor on its own. But together, they create resistance. Not visible resistance. Structural resistance. Which is why these homes don't disappear, but they don't spread either. They exist in pockets, built by individuals willing to navigate the complexity. Proven in real conditions, but rarely translated into mainstream adoption. The limitation isn't whether they work. That part has already been answered. The limitation is how well they fit into everything built around them. And once that becomes clear, the question shifts again. Because it's no longer just about why they're ignored. It becomes something more fundamental. What happens when a house stops depending on the systems designed to support it? And what does that change? Beyond the walls themselves, there's a moment where the conversation changes. Up to now, the focus has been on performance, how the house behaves, how it reduces cost, how it operates differently from what most people expect. But once that's clear, the question isn't really about performance anymore. It's about consequence. Because when a house stops needing as much from the outside, it doesn't just change the building. It changes the relationship. In a typical setup, a home is part of a chain. Energy flows in, water flows through, waste flows out, systems cycle constantly to maintain balance. Every day, something is being consumed, adjusted, or replaced. That flow is so normal it becomes invisible. You don't think about the furnace turning on, you feel the warmth. You don't track the cost of each cooling cycle, you notice the comfort. The system works quietly in the background, and the house becomes something you depend on, through everything connected to it. Now, Remove part of that chain. Not entirely. Not completely disconnected. Just reduced. Less energy required, less forced heating, less mechanical cooling, water reused instead of immediately discarded, air moving without machines pushing it. At first, the change feels small, but over time, it compounds. The most obvious effect is financial. Lower bills, month after month, not because of a temporary adjustment, but because the demand itself is lower. Systems run less often, equipment lasts longer, external inputs shrink. The 80% reduction isn't a one-time outcome. It's a new baseline. And once that baseline is set, something else begins to shift. Predictability. In conventional homes, costs fluctuate, energy prices change, usage varies with seasons, maintenance appears unexpectedly. There's always some level of uncertainty built into the system. But when the structure absorbs more of that variability, the swings become smaller. The house doesn't react as sharply to external changes. So the experience inside becomes steadier, not just in temperature, but in cost. Then there's dependency. A standard home relies on continuous input to function at a certain level of comfort. Remove that input, and performance drops quickly. In these systems, the drop is slower. Not because they're isolated, but because they're buffered. If energy supply is interrupted, the interior doesn't immediately follow. The stored conditions inside the structure carry forward. The house continues operating within a stable range, even as the outside system fluctuates. That changes how risk is experienced. Not eliminated, but softened. Maintenance shifts as well. When systems run less frequently, they wear less. When fewer components are required to maintain balance, there are fewer points of failure. The complexity doesn't disappear, but it redistributes from active systems to passive structure. That kind of shift is subtle. You don't notice it day to day. But, over years, it becomes visible. Fewer interventions, longer intervals, lower, cumulative effort. And then there's something less tangible, a psychological adjustment. In a system where everything depends on continuous input, there's an underlying awareness, often unspoken, that stability comes from outside. Energy must be available, services must continue, systems must remain intact. The house doesn't hold itself together. It's held together by what feeds it. When that dependency is reduced, the perception changes. The house begins to feel less like a node in a network, and more like a self-contained environment. Not isolated, not independent, in an absolute sense, but less exposed. And that difference, even if it's subtle, changes how people relate to the space they live in. So why does that matter? Because housing isn't just about shelter. It's about structure. Not just physical structure, but economic, behavioral, and systemic structure. Most modern housing is built around continuity. Continuous consumption. Continuous service. Continuous interaction with external systems. That continuity supports entire industries. It shapes how homes are financed, valued, maintained, and understood. Now introduce a model that reduces that continuity. A house that still functions, but demands less along the way. It doesn't break the system, but it doesn't reinforce it either. And that's where the idea of being ignored starts to make sense. Not as a deliberate decision, not as something hidden, but as an outcome. Systems tend to scale what fits them. They refine what aligns with their structure, and they move more slowly around things that don't. A house that reduces bills by 80% doesn't fail the test of performance. It passes it, but it changes the balance of what comes after. And that change doesn't always translate easily into widespread adoption. So the question at the beginning, why is it ignored, doesn't have a single answer. It's not one barrier. It's alignment, or more precisely, the lack of it, between what the house does and what the system expects. And once you see that, the story shifts again. Because it stops being about recycled materials, or thermal mass, or airflow design. Those are just tools. The real idea sits underneath all of them. A house can be designed to solve problems internally, instead of exporting them outward. It can reduce the need for constant correction. It can smooth out extremes instead of reacting to them. It can operate with less input, less intervention, less dependency. That doesn't make it universal. It doesn't make it the right choice for every situation. But it does change what's possible. And once something becomes possible, even if it sits at the edges, it quietly redefines the baseline. So the 80% number isn't just about savings. It's a signal. A signal that the way housing is typically approached is not the only path. That efficiency doesn't always come from adding more systems. Sometimes, it comes from removing the need for them. And when that happens, the question isn't just why it's ignored. It becomes something else entirely. What would housing look like if that idea moved from the margins to the center? And what else, quietly accepted today, would start to feel just as out of place as that original number?